guys, welcome back to SciMath, and today we're going to be talking about the op-amp closed loop voltage gain, which is VO over VI, where VO is the output voltage and VI is the input voltage. So let's get started. This is our first op-amp circuit that's given to us, and the question wants us to derive the closed loop voltage gain, which is VO over VI for this op-amp circuit. So the first step in this is to first of all know what the circuit is basically showing. And so here we can see we have two resistors here, R1 and R2, connected like a voltage divider, because right here we have this node, which I'm going to label as Vx, right? This node here in the circuit Vx is connecting R1 and R2 in as like a voltage divider, right? And because it's two resistors in series and the common node voltage point is Vx, and so I labeled that. Vi is the input voltage, right? And there's an infinity symbol in the op amp, which means that this is an ideal op amp. Okay, so whenever you see an infinity symbol in there, that means it's an ideal op amp. With an ideal op amp, the assumptions we can make are that V minus is equal to V plus, and I'll explain what this is, and also I minus is equal to I plus is equal to 0. Okay. Well, 0 amperes. So basically, these are the two conditions that we can, assume with an ideal op amp. The first is V minus is equal to V plus. That is basically this point right here. The voltage here, right here, this is V minus, and this is V plus. So it's basically the voltage. So the in the op amp, this negative symbol here, the minus sign, that's the inverting input side, and the positive one is the non-inverting input side of the op amp. And basically the reason we call it a closed loop voltage gain is because we have this negative feedback loop that is closing the circuit. So like it's this closed loop with this R3 resistor here, and it's a negative feedback because this resistor is connected to the inverting input terminal of the op amp. And then VO is just the output voltage that's coming from this circuit configuration. So now that we've identified V minus and V plus, and we know that the two assumptions that we can make with an ideal op amp, when we see the infinity symbol, is V minus is equal to V plus, and the second one is I minus is equal to I plus is equal to 0 amperes. Basically, it's saying that the current at these two points, right, of the circuit, like no current enters the inverting terminal, and no current can go through the non-inverting terminal as well. So the current, we can always say that the current right here and here is 0 amperes, right? So there's no current there. And so basically what that means is that the current coming from here will always go from here. It'll start, right? And then it'll go this way. All the current will go this way, and nothing will go here, and there is nothing here. So the first step now that we always do with op amps is whenever you see an op amp, just do KCL. It's the easiest way, especially with these questions of like deriving the, gain. And gain, always remember, gain is dimensionless. There are no units to gain. So once you solve it, if your answer has units in it, that means it's wrong. It should be dimensionless. There should be no units to the gain. So first, let's start doing KCL at V sub x. V sub x, the node V sub x, correct? So the way we do KCL is we see the currents that are coming in and the currents that are leaving that node. So when we look at Vx, which current is entering here? Let's say the one through the current through resistor 1 is I1, correct? And so the current is coming here, but then at this node, the current splits and goes this way and this way through our 2 resistor. So we can call this current I2, and we can call this current that's going here as I3. And we know that all the current will go, the I3 will go all the way here in the negative feedback and not here because of the ideal op amp assumption that no current can get through to the inverting and non-inverting terminals of the op amp. So now what we do is we basically do the KCL. And so the way we do KCL is we see, okay, we look at the current. I1 is going from VI to VX, which means VI is at a higher potential than VX because current always flows from high potential to low potential. So that means VI is at a higher potential than VX. So we know from Ohm's law that I is equal to V over R, and so that's basically what we're doing. We're going to do here VI minus Vx because from the high potential to the low potential all over R, which in this case it's R1, correct? The resistor. Next, we want to see what is let's assume that I3 is not that way. Let's assume that it's going in the opposite direction, okay? Because that'll make it easier. Okay, so we'll say I3 as this, okay? So now entering. So we're still at the entering side, so let's put a plus there, and now we see, okay, I3 is going in this direction, so that means it's going from VO, V naught, whatever, VO, to VX. So that means VO is at a higher potential than VX. So we do VO minus VX over the resistor it's going through is R3. So we say R3 over R3, correct? Next, that's all the currents that are entering, I1 and I3. Now we consider equal to, because KCL, it basically says all the currents entering a node equal all the currents leaving that node. So now which current is leaving? It's only I2. And I2 is going from VX, the node VX, to this symbol here is the ground. So that just means 0 volts. So we can essentially say, Vx minus 0. We don't even need to write that 0 because we know this is ground. So once you know that, you don't really need to write the 0. So, and then over R2 because that's the resistor it's going through. When we solve this out, we know we want to get VO over VI. So let's see. So basically the way to solve this is we can see that now what we have to do, we have to use the second the first assumption that we made for an ideal op amp, which is V minus is equal to V plus. So here we can see that V plus, it's the positive terminal of the op amp, is grounded. That means V plus is 0 volts. And according to the assumption, we said V plus is equal to V minus or vice versa, right? So that means in this case here, V minus is equal to V plus is equal to 0 volts. Just because the V plus, the positive terminal of the op amp, is grounded. And V minus and Vx, that's the same. This wire here is still the same. So that means that makes Vx 0 volts as well because the voltage can't change in between here, obviously, So it's like the same at this point or at this point. So Vx, automatically, that makes it 0 according to this ideal op amp assumption that we made, right? And that makes it very simple because then the equation just becomes Vi minus Vx is 0. So Vi over R1 plus VO minus Vx, where Vx is again 0. So VO over R3 is equal to just 0 because Vx is 0. So this whole Vx over R2 just becomes 0, correct? So now this just becomes a matter of, solving. And so what we can do here is next, from this equation, we can go, okay, let's keep the VO over R3 on one side, take the VI over R1 to the other side. From that we get minus VI over R1. And now we want VO over VI, keep in mind, because the gain is VO over VI. So from here I can take R3 to the other side, I can multiply, and we would get VO is equal to negative R3 over R1 times VI. And now we just take VI to the other side, and so we get, therefore, VO over VI is equal to negative R3 over R1. So that is the closed loop voltage gain for this op amp configuration. It's negative R3 over R1. And basically what it is telling us is that this resistor here, R2, does nothing to affect the gain, the voltage gain. And so it doesn't affect, basically it's there, but it's still grounded, so it doesn't really affect anything. And so that's why our gain is negative R3 over R1. So So that was the first op amp. Now let's do another op amp configuration. So this is the second op amp circuit configuration, and as you can see, all we've done here is we've kept R1 where it was, we've kept R3, it's still a negative feedback loop and a closed loop. You know, we're gonna get a closed loop voltage gain. The only thing we changed was we shifted R2, the resistor, from being here to here at the output side. So it's coming right here at this, where the output voltage VO is. And so that's where R2 is, but it's still grounded. And so now how this changes things is we still have this node right here, correct? We have this node right here, and this is basically the V minus node. And the V, we can label, let's just label this again as Vx, right? And we have this as Vx. Now, we can do, like I said, whenever you have to derive, just with op amps, always do KCL. That's the number one thing. And so with KCL now, what we're going to do is we're going to do KCL at V of x again. So let's do KCL at V of x. What we get is, let's assume that the current, again, let's assume the same directions where I1 is entering Vx, I3 is also entering Vx, and again, let's just do I2 as, yeah, like right here, right? So, well, basically, at this point, I2, in this circuit, we don't care about the current I2 because it's not even at the node Vx here anymore. It doesn't really matter, and it's not affecting. The only currents that are entering the node Vx is I1 and I3, and nothing is leaving. So that's basically zero, because we said KCL is the sum of the currents entering a node is equal to the sum of the currents leaving the node. So when we do KCL at Vx now, we get, so I1 is going from Vi to Vx, so it's Vi minus Vx over R1 plus, this is going from VO minus Vx over R3 equals 0, right? That's the equation we get. And now the same thing happens. If you think that the resistor being here makes any difference and that we have to do, you know, because I did make like 2 dots here basically to symbolize, but if you think that this resistor R2 here is going to affect, or we have to consider it in any way, it doesn't, because it's not even connected to Vx in any way. So when we do KCL, we assume the same thing again because we know V plus is 0. We said that, right? We said before that V plus is 0 volts. That makes it equal to V minus. And V minus is basically Vx here in this case. So Vx is 0. Vx is 0 volts. Now we know Vx is 0 volts, so when we, you know, simplify this again, we get Vi minus 0 over R1 plus VO over R3 equals to 0. And now when we do the whole simplification process again, it's the same equation that we ended up with last time, you know? So I'd already solved it before in the first op-amp configuration, so you can rewatch that if you need to, but we basically, when you rearrange this equation to get the gain, which is VO over VI, we get negative R3 over R1 again. So that is the final answer. And what this tells us again is that the resistor, even though R2 is here, the resistor R2, it doesn't affect the voltage gain at all because the voltage gain is still the same. It's negative R3 over R1. So that's it for op amps and how to find the closed loop voltage gain, how to derive them using KCL. Always just do KCL with op amps. It's the easiest way. And I hope you learned something new and enjoyed learning it. If you did, don't forget to like, share, and subscribe. And always remember to stay curious and keep learning. Thanks for watching.